Welcome to Domain 3 of the Security Plus Exam Cram series, 2024 edition. And here in Domain 3, we'll kick things off with a look at the security implications of different architecture models. Before we explore applying our knowledge of security concepts and principles to securing enterprise architecture. Then we're going to compare and contrast strategies for data protection. And we'll wrap things up with a look at the importance of resilience and recovery in security architecture. And as always, I'm going to take you line by line through every item mentioned in the official exam syllabus. Lots to cover here in Domain 3. Let's dig in. You'll find a PDF copy of this presentation available in the video description, intended for you to download and use in your exam preparation. And the chapters within this course should appear automatically on the timeline, but just in case, you'll find a table of contents that's clickable in the video description, so you can hop forward and back in the video as necessary as you prepare. And as with the previous release of the Security Plus exam, I recommend the official study guide from Cybex, which includes 500 practice questions, 100 flashcards, and 2 practice exams, as well as the companion practice test manual, which brings another 1,000 practice questions and 2 practice exams. And if you register for the online resources so you can leverage these questions in an electronic format, I believe it's all the practice quizzing you're going to need to prepare yourself for exam day. And I will leave you links in the video description to the least expensive copies on Amazon.com. The focus of Domain 3 is security architecture. And as always, we're going to go line by line through the official exam syllabus, touching on every topic we see there. In section 3.1, we'll focus on architecture models. More specifically, the syllabus asks us to compare and contrast the security implications of different architecture models. And the architecture and infrastructure concepts here definitely cover a lot of cloud technology. We'll look at the shared responsibility model called the responsibility matrix in this syllabus. And we'll talk about hybrid considerations, think hybrid cloud, very common model in the enterprise. And we'll touch on a variety of concepts from infrastructure as code, serverless, microservices, and then various aspects of physical and logical networking and network segmentation. We'll touch briefly on the case for on-premises, but we'll dig into virtualization, containerization, and some specialized systems or embedded systems like IoT and real-time operating systems. And we'll touch briefly on industrial control systems and supervisory control and data acquisition systems, ICS and SCADA. And we'll wrap this session with a look at a long list of considerations. So really think about all of these infrastructure and architecture concepts as the what, and these considerations as the why as we're going through the design process. And since the focus here is the security implications of different architecture models, we're going to dig into some of that strategy, some of the why we would choose these various architecture and infrastructure models. We're going to start with cloud models and cloud service models and the shared responsibility model, what they call the responsibility matrix in the syllabus. Cloud's a big topic. It can feel a bit overwhelming if you're not already experienced, so I'm going to give you what you need to pass the exam, but I'm also going to ground you in the basics around cloud models and service models and how responsibility factors in security. Very important for this exam. So let's start with cloud service models. You'll see some familiar terms here, starting with infrastructure as a service. The customer is responsible for configuring the VMs, virtual network, the guest OS security, all as if the system were on premises. But the CSP, the cloud service provider, is responsible for physical host, physical storage, physical network, and securing all the above. We're handing off management and security to that vendor. Next, we have platform as a service, where the CSP is responsible for the physical components, the internal network, and the tools provided. This is typically even less expensive for the customer, but we have less control in that case. And then finally, we have software as a service, where the customer remains responsible for configuring access to the cloud service for their users, as well as shared responsibility for data recovery. In a SaaS solution, typically the provider is going to give us a way to recover data, but we may implement our own data recovery so we can recover data faster. And I'll give you an example here in a minute. But the CSP owns physical infrastructure as well as network and communication. Now I'm going to give you a visual tour of the responsibility matrix, the shared responsibility model, as well as a couple of examples for context. And in terms of responsibility, we'll show the CSP in gray, the customer in blue, and shared in light blue. On premises is quite simple. Responsibility is 100% the customer. You own it. This is also where private cloud lives. So getting back to our model here, we have infrastructure as a service where you see the CSP begins to take on some responsibility for the physical networking, storage, servers, and virtualization. So they're managing from that hypervisor down. When we move into platform as a service, the CSP takes on more responsibility still, now managing the operating system, the middleware, and the runtime, with the customer only managing data and applications. And then when we move into software as a service, you see the customer now only retains shared responsibility for data and applications. And of course, they would manage access. So let's break down the responsibility for each of these. So when we look at infrastructure as a service, the CSP provides the building blocks like network, storage, and compute. And the CSP manages staff, hardware, and data center. So in this model, we have examples like Azure Virtual Machines, Amazon EC2, and Google Cloud Platform's Compute Engine. Moving on, we have platform as a service. And here, the customer is responsible for deployment and management of apps, and the CSP manages provisioning, configuration, hardware, and operating system. Examples here include database as a service like Azure SQL, API management, Azure App Service where we host web apps. So platform as a service gives us a platform for the building blocks of data and applications without the worry of managing any of the components beneath it. And then we have software as a service. So the customer just configures features. The CSP is responsible for management, operation, and service availability. The customer has some responsibility in access management and data recovery. If the customer grants one of their users too much access and that user maliciously or accidentally deletes a bunch of data, that's not the CSP's fault. Granted, they'll typically have a feature built in that offers some help in recovering that data, but it's still not their fault. Some examples of software as a service. What we'd historically know as Office 365, ServiceNow, and Salesforce, 3 good examples. Next on the agenda on the syllabus is hybrid considerations, but I think you really need to understand all cloud models to appreciate the advantages of hybrid. So we'll cover them all here briefly and you'll be all set. So we'll start with the benefits of cloud computing. So the cloud is cost-effective, global, secure, scalable, elastic, and always current. We have the public cloud where everything runs on the cloud provider's hardware. So there we're talking about AWS, Azure, Google Cloud Platform. Your advantages here include scalability, agility, pay-as-you-go capability, paying for only what you use, no maintenance, and low skills. Customers are responsible for less, so they have to know a little less, so it's easier to take advantage of public cloud. Next we have private cloud. This is a cloud environment in your own data center. A cloud environment dedicated to a single customer. Certainly some advantages here. Legacy support, control over the environment, compliance with any regulatory obligations is going to be easier. It definitely provides greater control of upgrade cycles and legacy apps in some compliance scenarios. So if I have a mission critical app that supports my manufacturing floor and that application is out of support, I'm probably not going to be able to get it in the cloud, but I can still run it in my data center if I'm willing to accept the risks that go along with it. In other environments still, maybe I want physical isolation of a fashion that I can't achieve in the cloud. Private cloud's going to be a great answer. Next we have the hybrid cloud, which combines public and private clouds, allowing you to run your apps in the right locations. The advantages here, first and foremost, are flexibility in legacy, compliance, and scalability scenarios. It enables the organization to control the pace of public cloud adoption. Every time they deploy a new app, they can choose whether that app lives in the on-premises data centers or in the cloud. And we have the community cloud. This is a less frequent model, but it's similar to private clouds in that they are not open to the general public, but they are shared by several related organizations in a common community. That's what makes them different from a private cloud. I don't see community cloud deployed much. And then we have multi-cloud. This combines resources from 2 or more public cloud providers. It allows organizations to take advantage of service and price differences, but at the cost of added complexity. Frequently, the management controls are different. The security needs don't align 100%. So there are some design exercises you'll have to undergo twice for each of these platforms when you have 2 or more public cloud providers. Now we'll move on to third party, and I want to talk about the logical versus the physical here because a cloud service provider is a third party vendor. And we're really dealing with the logical design of a data center. It's an abstraction. We're not so much worried about physical servers. If we look back at the now legacy colo scenario or colocation, customers were separated at the server level or the cage level. If you've never seen a colo scenario, a cage would typically house multiple servers for a customer, and it would be a locked cage. So in a logical data center design in the cloud, customers utilize software and services provided by the CSP. So the logical design of the cloud infrastructure should create tenant partitioning or isolation, should limit and secure remote access, monitor the cloud infrastructure, and allow for the patching and updating of systems. So the CSP here is focusing on tenant partitioning and access control in the logical sense. Because that infrastructure underneath our logical, all the physical servers, network, storage, etc. is multi-tenant, it's shared. So let's talk about that word, multitenancy. So logical isolation in CSP multi-tenancy makes cloud computing more affordable, but it creates some security and privacy concerns. If isolation between tenants is breached, customer data is at risk. And multi-tenancy is a concept that was created decades ago. Business centers physically housed multiple tenants. Colo data centers supported multiple customers. But the risk in these scenarios is largely physical. As I mentioned, customers were separated by servers, racks, cages. They weren't using the same physical infrastructure. In the public cloud, tenant partitioning is largely logical. Customers are sharing capacity across the CSP data center, including all the physical components. And the CSP and the tenant, the customer, share responsibility for implementing and for enforcing controls that address the unique multi-tenant risks of the public cloud. The CSP is going to make sure customers are isolated. Customers have to configure access control around their own resources. So in infrastructure as a service, the CSP makes sure that there is isolation from the hypervisor down, but the customer is responsible for configuring access to their own virtual machines. Their Office 365 instance is isolated, it's only theirs. The customer has to configure access to that Office 365 instance, or that Salesforce instance or ServiceNow instance. All comes back to shared responsibility. And as you move on from Security Plus to higher level, more difficult exams, CISSP, CCSP, understanding shared responsibility and responsibility for security will be very important. All right, let's move on to infrastructure as code. Infrastructure as code is the management of infrastructure, networks, VMs, load balancers, connection topology described in code. And just as source code generates the same binary every time, code in the infrastructure as code model results in the same environment being deployed every time it's applied. And it's a little better than that, I'll explain in a moment. Infrastructure as code is a key DevOps practice, and it's used in conjunction with continuous integration and continuous delivery, commonly known as CI/CD. Infrastructure as code is very common. It is the standard in the cloud. We're always deploying environments and components from infrastructure as code and often through CI/CD pipelines on our DevOps platform. To appreciate infrastructure as code, there are two distinct characteristics of infrastructure as code that improve resiliency in the IaaS and PaaS service models that you need to understand. Infrastructure as code is declarative, or declarative, depending on how you'd like to pronounce it, which means IAC must know the current state. It must know whether the infrastructure already exists, to know whether to create it or not. Now, when we look at legacy scenarios like simple scripts, imperative deployment methodologies are unaware of current state. Not the case with infrastructure as code. Infrastructure as code is also idempotent, meaning deployment of an infrastructure as code template can be applied multiple times without changing the results. So for example, if the infrastructure as code template says deploy 4 VMs and 3 VMs already exist that are defined in that template, one more VM is deployed. If I delete 2 VMs and run the template again, it will deploy 2 VMs. And if it sees that 4 VMs exist, it will deploy 0 VMs. But it makes sure that the state declared in that template has been deployed in the environment. So I want to give you just a bit of context. So these characteristics help reduce errors and configuration drift. It takes human decision making and manual steps out of the process. And if we're worried about configuration drift, that something unwanted has been changed, we can simply apply the template again. So for context, let me just show you a quick example of infrastructure as code. Again, Security Plus is vendor agnostic, but this will give you a taste of what I'm talking about. So I have an Azure subscription. I'm going to switch over to my lab environment here. I'm looking at a virtual machine. My virtual machine here is PZ-Win10 Gen 2, and you can see settings like the disk. I can see networking, security, backup features, etc. I'm going to go down here to the automation category, and I will look at, under automation, I will look at export. So when I click export template, it's going to run for a couple of minutes generating a template, and here we have it. And if I scroll through this, what you see is a JSON template. And if I scroll through this template, it defines characteristics like the name, like the disk, like the VM template, the size of the VM, how many cores am I getting, how much memory. And as I scroll down, the network configuration, what region, I see location here, it's deployed in the central US. I see the operating system SKU. So even though I deployed this virtual machine in the console, they're giving me the capability to create the infrastructure as code template so I can reproduce this every time without manual steps if I wish to do so. And if I'm a DevOps engineer, I'm going to learn the language. I'm going to learn how to define infrastructure as code in templates like this, but I can also, as you see, just go into the portal and it will do some of the work for me. And extrapolate that out to entire environments. I can deploy entire clusters with application front ends and databases and paths and elaborate networks, all expressed as code, along with their security settings. All right, enough of that. I hope that gives you a bit of context if you're not experienced in cloud yet. Let's move on to serverless. So in a serverless architecture, it's a cloud computing execution model where the cloud provider dynamically manages the allocation and provisioning of servers. It's hosted as a pay-as-you-go model based on use. Resources are stateless, the servers are ephemeral, and they're often capable of being triggered. An example here would be function as a service, where I have a function, a block of code, and I trigger that code, I give it an input, it produces an output, and it only runs on demand. So to appreciate serverless, I think it will help if we look at the difference in responsibility and execution between serverless and platform as a service. So let's talk about what they have in common and how they are different. So on the left I have platform as a service, on the right I have serverless. Now in both models, devs do have to write code. There's no server management, but there are some distinct differences as well. So in the PaaS model, we have more control over the deployment environment. We have less control in serverless. In platform, the application has to be configured to auto-scale. On the serverless side, the application scales automatically. You might have some minor responsibility to select the right SKU, but it's going to scale automatically. And on the PaaS side, the application takes a while to spin up, while on the serverless side, application code only executes when it's invoked, which means on the whole, it is typically running less, which means it's going to be more efficient in terms of compute and, generally speaking, less expensive. It is eliminating the need for polling, some sort of little process just checking repeatedly to see if it needs to run, because it executes only when invoked. So that's the advantage, or the advantages, of serverless. Moving on to microservices. So microservices are fine-grained services with a discrete function. So in plain English, they're code modules designed to perform one function very well. Services are loosely coupled and technology agnostic, which enables services coded in different languages to communicate. Each service is deployed, operated, scaled, and updated independently. So dependencies between services are minimized wherever possible. So let me share an analogy, just an example that can paint a picture of how an e-commerce application built with microservices might be structured, just for context. So we have a product service. This service manages product information, including adding, editing, and retrieving product details. We have the cart service that handles user carts, adding and removing items, and calculating their totals. The order service, which processes orders, handling payments, and managing order fulfillment. And a user service that manages user accounts, authentication, and user profiles. Each service has a discrete function. It can be written in whatever language it needs to be written in. These services can make calls to one another in the context of delivering this larger service. This is very much parallel to how things evolved at Amazon, growing from a startup to the largest e-commerce provider in the world. Microservices were the norm. In fact, Jeff Bezos at one point said if you build a service, that service needs to be consumable by other teams so they don't have to build the same service over again. So that model greatly reduces duplication of effort and allows an organization to grow more quickly and more securely. This architecture model greatly reduces the attack surface. You're really just exposing that service as an API. Moving on to physical isolation, we see air gap called out again, a topic we've discussed previously in this series. It's the practice of physically isolating a computer, a network, or a device from any external connections, including the internet or even other internal networks. It creates a barrier similar to an air gap in plumbing, preventing malicious actors from accessing the system, and thus its name. Air gap systems are common in high sensitivity scenarios in financial services, with medical devices, military networks, and industrial control systems. But air gap means physical isolation. Logical segmentation is also called out, which is segmenting the network without additional physical hardware. So in this category, we have VLANs, which logically segment a local area network into subnetworks. It happens at layer 2, where network switches operate. We have VPNs, creating an encrypted tunnel between devices or networks to pass traffic, including protocols like IPsec typically. And when we look at hybrid cloud and public cloud environments, we'll often see an IPsec VPN used to connect on-premises to the cloud network, or even to peer virtual networks within a cloud. We have virtual routing and forwarding, which allows a single router or switch to function as multiple virtual routers or switches. And subnets divide larger IP ranges into smaller ranges. And subnets divide larger IP ranges into smaller ranges, which routers can then segment using access control lists, or ACLs for short. Software-defined networks is also here in the logical category. So this is a network architecture approach that enables the network to be intelligently and centrally controlled or programmed using software, and has the capacity to reprogram the data plane at any time. SDN is pretty common in software-defined local area networks and even software-defined wide area networks. But it separates the control plane from the data plane, opening up a number of potential security challenges. SDN vulnerabilities include man-in-the-middle attack and potential denial of service from within the network. We would secure communication with TLS wherever we can. And because SDN happens in software and code, it supports infrastructure as code, CI/CD, DevOps, the deployment automation that literally every enterprise uses in the cloud today. So I want to give you a quick visual. I mentioned the data plane, so I want to show you the three planes. We have the control plane. This is where your SDN controller lives. We have the management plane, where the applications reside that we use to configure the control plane. It's our device and networking configuration. And then we have the data plane, where our switches reside. So the control plane interfaces with the management plane on the northbound interface, and with the switches on the southbound interface. The northbound interface ensures only trusted authorized applications access critical network resources, and then through the southbound interface, the open flow protocol interfaces with devices, which are ultimately responsible for forwarding the data packets through our network. Next, we have on-premises versus off-premises, so we'll look at the advantages of each. So on-prem, the organization retains complete control of the full stack. We talked about this in private cloud. This can be beneficial in legacy and compliance scenarios because we have full control of patching, upgrades, data residency, data security. And off-premises, whether we're going to the cloud or a colo facility, it offloads at least some of the responsibility for infrastructure and many utilitarian management functions to the service provider. The cloud service provider is really what's top of mind here, moving from on-prem to the cloud. More time and budget to focus on delivering business value because we're not doing all the care and feeding for the infrastructure. And there's something else that we need to talk about here when it comes to on-prem versus off-prem. So when we're thinking about cloud versus on-premises, there's certainly a change in how our budgeting goes. So a business purchases and maintains its own servers in a data center when they're hosting on-premises. So there's a lot of upfront investment. Moving to the cloud is going to shift some responsibility over to the cloud service provider. Most notably, a lot of that infrastructure investment that the organization was doing can go away. And so what happens when organizations adopt the cloud at scale is it shifts IT spending from capital expense, what we call CapEx, over to operational expense, OpEx. So we're now paying for what we use, paying as we go, rather than going through budgetary cycles where we have to get approval and chart our course months or even years in advance for these major investments. Definitely cloud is going to factor a little more prominently than in the previous version of this exam, so I'd know the advantages of cloud and on-premises for the exam. We talked about everything you need to know for the exam in cloud models and the responsibility matrix earlier in this session. We also see centralized versus decentralized on the syllabus, so understanding the advantages of each. So in the centralized model, we have infrastructure and equipment located in one or a small number of large data centers. This can often reduce cost and management, but it potentially increases the impact of a data center outage because we're going to have a greater percentage of our compute in any given data center. Where with the decentralized model, we have equipment spread across a larger number of locations, which can increase cost and complexity, but it decreases the impact of an outage at a single location. Decentralized may also give us advantages in improving efficiency or user experience because we can have resources nearer our employees or content nearer our customers. Up next is containerization. So this is a lightweight, granular, and portable way to package applications for multiple platforms, and it reduces the overhead of traditional server virtualization, of VMs, by enabling containerized apps to run on a shared OS kernel. Containers don't actually have their own operating system, so they're sharing a kernel with all the other containers, though the app within the container doesn't know that. Now, containers do share many concerns of server virtualization. Isolation at the host, process, network, and storage level, all still concerns. But they can be used to, in some cases, isolate existing applications developed to run in a VM with a dedicated operating system. If you're working in containers, it's probably with Docker or more likely Kubernetes, but we'll circle back to that in a moment. Let's take a look at why we'd want to containerize in the first place. What's the advantage? So here I have a Type 1 hypervisor, a bare metal hypervisor like ESXi, KVM, or Microsoft Hyper-V. So let's look at this hypervisor in a virtualization scenario with a VM, where each VM has its own OS kernel and memory. But we look at a container host where the containers are isolated but share a single OS kernel as well as binaries and libraries where possible. So it's about the density. See, each VM has its own OS kernel and memory. It results in more overhead. We can fit fewer VMs on there where containers are isolated, but they share that single OS kernel and as a result use fewer resources. So if we containerize our applications, we can fit more instances on to a single virtualization host, which means greater density, which means more compute for our money. So just unpacking that a bit further, a container platform like a Docker or a Kubernetes needs orchestration, basically a scheduling controller, network and storage, the container host, which is the hypervisor server, the hypervisor host, container images. Think of container images as the equivalent of virtual machine templates, and then a container registry, a place where we store our container images. But as you can see in the diagrams here, the isolation is logical, isolating processes, compute, storage, network, secrets, and the management plane on the whole. Let's talk about adoption of container compute in the real world in case you haven't experienced this yet. So generally speaking, it's going to be with managed Kubernetes, which is the de facto standard for containerization today. Container hosts are cloud-based virtual machines. This is where the containers run. And most of your cloud service providers offer hosted Kubernetes service, which handles critical tasks like health monitoring and maintenance for you. It's platform as a service, basically. You pay for the agent nodes within your clusters. Those are the nodes where your containers run. You don't pay for the management cluster, a separate management cluster. They take care of that for you. And your major CSPs all offer some monitoring solution that will identify at least some potential security concerns. So from a security perspective, this is attractive because it allows organizations to move from on-prem to the cloud and consolidate their applications to fewer virtualization hosts. Less to manage and less to secure. And like I said, containerization shares many of the concerns of server virtualization, but we're enforcing isolation of network data and storage at the container level. So a tighter boundary, a more granular boundary at the very least. And when we look at the CSPs, Microsoft has what they call AKS. There's EKS in AWS and then GKE on the Google platform. A lot of acronyms there. Let me unpack those for you. That's Azure Kubernetes Service that runs on Microsoft Azure, Elastic Kubernetes Service that runs on AWS, and Google Kubernetes Engine that runs on Google Cloud Platform. Those are the advantages. That's the motivations for folks adopting containerization, and now you have a bit of a picture as to how this plays out in the real world in case you encounter it on the exam. Let's shift gears and talk server virtualization. This is the process of dividing a physical server into multiple unique and isolated virtual servers, virtual machines, by means of a software application, which is the hypervisor. Two security concerns that are top of mind in server virtualization are VM escape, where an attacker gains access to a VM and then attacks either the host machine that holds all the VMs or the hypervisor or any of the other VMs, which may belong to other consumers. So to defend, we want to make sure patches and hypervisor and VMs are always up to date and guest privileges are low. Server level redundancy, host intrusion prevention and detection are also effective. And the other is VM sprawl. This is when unmanaged VMs have been deployed on your network, and because IT doesn't know it's there, it may not be patched and protected and is thus more vulnerable to attack. So really avoidance is important here. Enforcement of security policies for adding VMs to the network, as well as periodic scanning to identify new virtualization hosts. Just in case it pops up, I want to cover the difference between the Type 1 and Type 2 hypervisors so you've got them straight in your head. We've got the Type 1 bare metal hypervisor, ESXi KVM Microsoft Hyper-V, where there is no operating system on the host. It's the hypervisor running on the bare metal. Then we have Type 2, the hosted hypervisor we call that. That's where there is a host operating system in the middle. So your hosted hypervisors would include VMware Workstation, Oracle VirtualBox, Microsoft's Virtual PC. And let's just cover some basic characteristics quickly here so you have the use cases in mind. So the Type 1 hypervisor, the bare metal, has a reduced attack surface as compared to the Type 2 hypervisor because it doesn't have that host operating system. This makes it more secure if implemented properly. It's commonly used for QA, load testing, and production scenarios, and is typically more expensive than a Type 2 hypervisor. So the Type 2 hypervisor, by comparison, if we just compare apples to apples, has an increased attack surface due to the host operating system. This makes it less secure versus Type 1, even if implemented properly. And this is really commonly used for individual development and lab scenarios. Developers and IT folks are using this for their own individual testing quite often. And it's generally less expensive than a Type 1 hypervisor for obvious reasons. With the increased importance of cloud in the world, I think it's less likely you're going to get a Type 1, Type 2 hypervisor question on the exam, but just in case, you're prepared now. So moving on, Internet of Things. So this is a class of devices connected to the internet in order to provide automation, remote control, or AI processing in a home or business setting. A couple of things to think about from a security perspective when you're choosing IoT solutions as your architecture. They often have limited compute resources. This affects your cryptographic options because you have less memory and processing power. Incidentally, if you get a question around that, elliptic curve is the answer. Smaller keys. And you often have limited ability to patch the embedded systems that make up these Internet of Things devices. Those are the two security concerns I'd keep top of mind. Okay, so let's talk SCADA. So a long acronym here, Supervisory Control and Data Acquisition, or Industrial Control System. So you'll often find SCADA systems in place where there is a large amount of industrial equipment. In an industrial, manufacturing, or public utility setting, equipment is often network connected and monitored, and it can be centrally configured, controlled, and monitored from a computer using a SCADA network. They usually do not have direct internet access for greater security. And because of their critical function, they should be segmented off from the rest of the network and protected by security controls to restrict access. You don't want the systems managing your water supply and your power grid connected to the internet. Next, we have the real-time operating system, RTOS. So smart devices like wearables and embedded systems, like in cars and industrial equipment, often use a real-time operating system. It's an operating system that's designed to work on a very deterministic schedule. This means that the hardware and software of the device is able to operate with very specific scheduling. Security of these devices is important, but it's often difficult to know exactly what's running inside some of those embedded systems. And so if you can't patch the system itself, if you can't keep it up to date, then you surround it with additional layers of security. You consider isolation. You perhaps have it behind a firewall. You have intrusion prevention and detection on the wire. But these systems process data immediately, and if a task or process doesn't complete within a certain time, essentially the process will fail. That's a real-time operating system. So I mentioned embedded systems here. That's the last one on the list in this section. The technology component of an IoT device is often referred to as an embedded system. It's really a full computer system embedded inside of another larger system. Examples here would include printers, GPS, drones, your VoIP phones in the office, modern vehicles, semi-autonomous vehicles. And again, these need to be patched and managed much like a computer. But if you can't patch, keep them up to date, add other layers of security. Firewalls, intrusion detection and prevention to reduce your exposure. Now we're going to move into considerations, and there are several that should be weighed as part of the architecture design and implementation process. So we've looked at a number of architecture and infrastructure technologies. Those are really the what we can select. Now we need to talk a bit more about why we would select it. So considerations can include resilience, cost, responsiveness, scalability, ease of deployment, transferring risk. All boxes we need to check as part of that design process, going through those considerations. Ease of recovery, patch availability, the inability to patch, power, compute. And as we're checking these boxes, certainly there are some technical considerations there, but many of these require input of the business as well. We need to tailor our solutions to security needs. Certainly if we have sensitive data, for example, we're going to raise the bar around data security. But if we have a service that needs to be available from 9 to 5 Monday through Friday, our design decisions, our architecture decisions, are going to be different than a service that needs to be available 24/7. So we'll step through these and unpack them one at a time, beginning with availability. So ensuring that a system or service is accessible to authorized users when it's needed. Targets will be set based on organizational needs and balanced against other factors like cost and security. We align our delivery with business needs to optimize costs. Again, not paying for 24/7 when we only need 9 to 5 or vice versa. Next, we have resilience, which is a subset of availability that focuses on the system's ability to handle disruptions without impacting availability. And by optimizing performance through outages or attacks, it ensures users experience acceptable response times during imperfect conditions. And we might build that resilience into the service itself, and if we can't, we may build that into security layers that sit in front of the service. Maybe I'm running a legacy app that is prone to SQL injection attack. That could have been prevented with secure coding practices, but we're past that point, so now as a mitigation, I'll add a web application firewall in front of that service, which will protect against SQL injection attacks. Next, we have cost, which includes financial expenses, your hardware, your software, your licenses, and your staffing, your personnel, and any other associated costs. And again, we want to strike the balance between cost, security, and functionality. Next, we have responsiveness. This refers to the system or service's ability to respond to user requests or events in a timely manner. Again, optimizing performance ensures the user experiences acceptable response times, and we strike a balance between performance and cost. Next, we have scalability, which refers to the ability to scale resources. We can scale vertically by adding more compute power to individual systems. We call that scaling up, or we can scale horizontally by adding more systems. We call that scaling out. We generally like to scale out in the cloud because it's less expensive. It reduces our run rate. It's crucial to support changing demands while maintaining availability, resilience, and responsiveness. Remember, availability is part of the CIA triad, one of our core goals of security. So scalability should protect availability and allow for future growth. Next, we have ease of deployment, which refers to the complexity and effort required to implement the solution. Complexity can increase initial costs as well as ongoing operation. We want to balance security with ease of deployment. Necessary complexity to make the solution secure, but not over-engineering to make a solution then difficult to operate or use. Next, we have risk transference. This describes when security risks are mitigated by transferring some responsibility to third parties through insurance, security contracts, or a service agreement. This enables the organization to mitigate critical risks too expensive or complex to address with their in-house resources alone. For example, they may not have the money on hand to rebuild a $10 million data center, but buying insurance to protect if that data center is destroyed through a natural disaster mitigates the risk. Next, we have ease of recovery. So recovery time and effort are crucial for availability and resilience, and complex solutions might necessitate additional investments in automation or redundancy to minimize downtime. Patch availability and vendor support. So we need to evaluate how often patching is required and the vendor's support responsiveness, because timely patching is essential for maintaining system security. And another condition we need to consider is the inability to patch. In high availability scenarios, patching might not be feasible due to potential downtime. And so in these cases, we have to consider alternative security measures like segmentation or intrusion detection to mitigate risks associated with unpatched systems. Next, we have power. Power consumption is a significant factor in data center design, and it contributes to ongoing service operations costs. Keeping the lights on in an enterprise data center is not cheap, and energy-efficient solutions can help reduce operational cost and environmental impact, and power is also built into the service or solution price in the public cloud. So again, if we decide a situation is not financially feasible, we look for a way to transfer responsibility, and that's what we do in the cloud scenario. And finally, we have compute, which drives ongoing cost, both in the cloud, where we're paying as we go, paying for what we use, and on premises, where we are responsible for all the cost, including hardware replacement. And so optimizing compute to manage cost and improve efficiency is going to be important. And that may lead us to choose one of these architecture models over another. For example, we might opt for that container solution because we can basically achieve greater density with our compute, optimizing our spend. And moving on to section 3.2, where we'll focus on security principles and enterprise infrastructure. More specifically, the syllabus asks us, given a scenario, to apply security principles to secure enterprise infrastructure. We'll explore infrastructure considerations, including devices, device connectivity, and device placement. We'll review network appliances. We'll explore port security, as well as an array of firewall types. We'll then move into secure communication and secure remote access before wrapping up with selection of effective controls. So devices and techniques to secure our infrastructure, how to communicate with our environment securely, and finally how to pick the right control for a given scenario. We'll start with infrastructure considerations, beginning with device placement. This is the decision of where to connect a device on a network, and it has significant implications in device exposure to potential threats. Factors that might influence our device placement decisions include the purpose or function of the device, the layout or segmentation of our network, traffic flow, minimizing hops, latency, and congestion by placing elements that communicate frequently near one another in adjacent segments or the same segment, and potentially other security or regulatory considerations. Next, we have security zones. So think of security zones as containment zones that prevent attackers who infiltrate in one zone from easily spreading throughout the entire network. Essentially, security zones limit lateral movement, so the damage caused by a security breach can be significantly minimized. Security zones also help to minimize the attack surface and mitigate potential consequences of security breaches. Common security zones include the intranet, extranet, and screened subnet. Let's dig into those three a bit deeper. The intranet is a private network designed to host information internal to the organization. Then we have the extranet, which is really a cross between internet and intranet. It's a section of an organization's network that has been sectioned off to act as an intranet for private network, but also serves information to external business partners or maybe even to the public internet. But at minimum, certainly a place where internal employees and business partners or contractors might collaborate or share information. And then we have the screened subnet, which is an extranet for public consumption, typically labeled a demilitarized zone or perimeter network. So screened subnet, DMZ, and perimeter network, three ways of saying the same thing. It creates a highly secure zone for critical systems that are public-facing. Next, we have the attack surface. So this consists of all the threat vectors that a system is exposed to. It includes all the ways an attacker might come after it. And our goal is generally to minimize the attack surface, which we can minimize with vulnerability management, network segmentation, access control, And finally, system hardening. So closing unused ports, disabling unused services, removing unused websites. So if we manage vulnerabilities, meaning keeping systems patched, for example, segmenting our network so we only allow systems that need to communicate to actually communicate, controlling access to those systems to personnel who need access. And if that's a system that needs to be customer facing, then customers need to be properly authenticated, and then hardening the system. Another consideration is connectivity. And connectivity is about the ability of devices and systems to communicate and exchange data with each other, potentially exposing systems to threats. So our goal is to establish secure connectivity, which means we are filtering traffic appropriately. If that's public facing, then we may be filtering through a firewall, a web application firewall, next generation firewall, network segmentation, access control, or the security zones that we described earlier. Also mentioned in infrastructure considerations are failure modes. Systems can fail open, which allows everything to pass through the system when it fails. No security controls are enforced, but there's no disruption to network activity. A system can also fail closed, in which case nothing can pass through the system when it fails, and no security controls are ignored, but network traffic is disrupted. So your first question might be, which option is best? Well, which option a system uses is made in the design phase, and which is best depends on use case priorities. For example, failing open would be good for an availability critical system, where availability is more important than enforcement of security controls. If failing open means temporary exposure due to lack of enforcement of security controls, but prevents some more severe consequence, then that's a good thing. And failing closed is good for safety and security-focused systems. For example, in a manufacturing scenario, if a system failure means that we're not going to have some physical security control in place that protects human safety, then failing closed is a good thing. And we see a handful of properties in the device attributes category, which I believe are intended to focus on intrusion prevention and detection, which is how I'll present them to you. Certainly they could have some other uses in the world of network devices, but I think intrusion detection and prevention was their intent. So we'll start with inline or in-band. This is when we would place network-based intrusion detection or prevention on or near the firewall as an additional layer of security. So in this case, the traffic passes through the device. Then we have the tap option, also known as out-of-band. So the network device replicates traffic for inspection. It provides access to a copy of network traffic while traffic continues on. This option eliminates the risk of device failure. And taps really come in two flavors, active and passive. Active taps require power to operate, and network ports are physically separate. There's no direct connection between them. Power outages will interrupt traffic. On the other hand, with passive taps, they have a direct path between network ports, and power outages will not interrupt traffic. Passive taps just copy the signal, where active taps may offer additional functionality. We see some network appliances called out on the syllabus. There's the jump server, which is typically placed on a screen subnet and allows admins to remotely connect to the network, generally used for secure remote administration. Then we have the forward proxy, which is a server that controls requests from clients seeking resources on the internet or an external network. This is typically used to filter outbound web traffic of your employees. And then we have the reverse proxy, which is placed on a screen subnet and performs the authentication and decryption of a secure session to enable it to filter incoming traffic. We see intrusion detection and intrusion prevention called out explicitly on the syllabus as well, so a few items we need to cover here. There's intrusion detection systems, which analyze whole packets, both header and payload, looking for known events. And when a known event is detected, a log message is generated, maybe an alert is sent, but that's basically it. Now with intrusion prevention, That system analyzes whole packets, both header and payload, looking for known events, but when a known event is detected, the packet is rejected. So it actively prevents malicious activity. So let's talk flavors of intrusion detection. Really, flavors of intrusion detection and prevention. So there's host-based IDS and IPS, which can monitor activity on a single system only. The drawback is attackers can discover and disable them. Host-based IDS or IPS is generally implemented in software, and disabling that may be as simple as killing a process or disabling a service. Network-based intrusion detection or prevention can monitor activity on a network, and network-based isn't as visible to attackers. In terms of scope, host-based monitors traffic reaching the host network adapter, its NIC, and network-based monitors the network's traffic. So some definite advantages to the network variety, though that is generally going to take more work to implement and will generally be more expensive. You want to be familiar with how these systems make their detections. There are a couple of types you should be aware of for the exam. The first is behavior-based, also called anomaly-based or heuristic-based, which creates a baseline of activity to identify normal behavior, and then it measures system performance and traffic against that baseline to detect abnormal behavior. The other option is signature-based, also called knowledge-based, which uses signatures similar to the signature definitions used by anti-malware software. So the behavior-based can detect previously unknown attack methods, where signature-based is really only going to be effective against known attack methods. But both your host-based and network-based IDS or IPS systems can be knowledge-based, behavior-based, or a combination of both. Load balancer gets a mention on the syllabus as well, and balancing load are multiple methods for building redundancy into network connectivity for systems and services. So one way is through network interface card or NIC teaming. Dual network cards paired together to give maximum throughput, and should one adapter fail, the other can ensure the server or the client maintains network connectivity. Then we have load balancers. Load balancers are typically hardware network appliances, though load balancing can be implemented in software, and it can balance multiple types of traffic across multiple servers. It will include some logic to determine server availability, everything from a simple ping to something much more sophisticated, like making a specific call to a server to ensure it's responsive as a measure of availability. And it's often used for web traffic, but it can support other protocols. Your Windows server platforms and Linux server platforms all support NIC teaming. And from a service availability perspective, load balancers can help maintain service availability during a cyber attack because it can continue to distribute traffic to the systems that are still available. So let's talk about that proper hardware load balancer. So a network load balancer is a device used to direct traffic, typically to an array of web or application servers or other service endpoints. So you could even put APIs behind it if you wanted to, quite typically. And there are several ways to set up a load balancer. You can do an active-active configuration where the load balancers act like an array dealing with traffic together as both are active at the same time. Bearing in mind that if all are active at once, a single load balancer failure may degrade performance if you have more than 50% capacity running through the pair. Active-passive is also common, where the active node is fulfilling load balancing duties and the passive node is listening and monitoring the active node. And should the active node fail, then the passive node takes over, providing redundancy. If you see the abbreviation NLB, that's a network load balancer. It's synonymous with the term load balancer. And the address you'll point clients to make their request through a load balancer is the virtual IP address. It eliminates a host dependency upon individual network interfaces. Web traffic comes from the load balancer from the virtual IP address on the front end, and the request is sent to one of the web servers in the server farm on the back end. So if I were to sketch out a picture, you've got your network load balancer, you have that virtual IP address on the front end. Your client requests are coming in to that virtual IP address. You can assign a DNS name to that IP address, and it will route the request back to an available server on the back end. So you've got your front end and your back end. So your load balancers also have scheduling options which determine how the load is distributed by the load balancer. So the scheduling algorithm may prioritize the least utilized host based on the status of the servers, the number of connections each is serving. It can use simple DNS round robin where it just starts with the lowest IP address and goes from server 1, 2, 3, and then back to 1. Affinity, where the load balancer is set to affinity, the request will be sent to the same web server based on the requester's IP address and potentially their port and potentially also their session ID. The affinity configuration in this case would be referred to in tuples. So an IP is a tuple, IP plus port is 2 tuple, IP, port, and session would be 3 tuple. This is also known as persistence or a sticky session, where the load balancer uses the same server all the way through for the single session, usually intended to ensure continuity of processing and a good user experience. Sensors also come up in the context of IDS and IPS in the syllabus. You can place a sensor on the network to alert the IDS of any changes in traffic patterns on the network. And if you place a sensor on the internet side of the network, it can potentially scan all of the traffic from the internet. Under port security, we see 8021X security, which is an IEEE standard for port-based network access control. It basically enables an authentication protocol for any devices trying to connect through the LAN or the wireless LAN. It's commonly used for enhancing network security by ensuring that only authorized devices can access the network through a specified network port. An authentication would happen through a radius server. So the authentication process has 3 parties involved: the user, the authenticator, and the authentication server. So the user and the authentication server, I think, are self-explanatory. You may ask, what is the authenticator exactly? Well, the authenticator, typically a network switch or wireless access point. An authentication would take place through radius, potentially checking with certificate authentication, for example, and only allowing known managed compliant devices on the wire or on the wireless LAN. Still in that port security category, right under 802.1x is Extensible Authentication Protocol, and there's a reason for that. It's an authentication framework that allows for new authentication technologies to be compatible with existing wireless and point-to-point connection technologies. But the reason it shows up there is 802.1x authentication relies on EAP, on Extensible Authentication Protocol, and there are actually variants here. There's Protected Extensible Authentication Protocol, which encapsulates EAP methods with a TLS tunnel that provides authentication and potentially encryption. And then there's LEAP, a Cisco proprietary alternative developed to address deficiencies in TKIP before the 802.11 WPA2 system was ratified. And there's a progression of EAP that leapfrogs the LEAP variety, which is why I wanted to show you that progression. So we have EAP Fast, which was developed by Cisco, used in wireless and point-to-point connections to perform session authentication, and it replaced LEAP, which was insecure. Then there's EAP TLS, a secure version of wireless authentication that requires X.509 certificates. The EAP TLS process involves 3 parties: the supplicant, which is the user's device, the authenticator, the switch or controller, and the authentication server, the radius server. There's a third variant, EAP TTLS, which uses 2 phases. The first sets up a secure session with the server, creating a tunnel using certificates that are seamless to the client. The second phase uses a protocol like MS-CHAP, that's Challenge Handshake Authentication Protocol, to complete the session. This was really designed to connect older legacy systems. All of these show up in various study guides. Where I would focus for the exam if I were you is 802.1x, we talked about a moment ago, which relies on EAP to deliver port-based network access control. You should be familiar with a few different types of firewalls for the exam, so we'll cover those here, starting with the static packet filtering firewalls. They filter traffic by examining data from a message header, and they operate at layer 3 and up. We have the application level firewalls, which filter traffic based on a single internet service protocol or application. They operate at layer 7 of the OSI model, which is the application layer. Circuit level firewalls used to establish communication sessions between trusted partners typically. They operate at the session layer, layer 5 of the OSI model. SOCKS is an example of a circuit level firewall. There's stateful inspection firewalls that evaluate the state, session, or context of network traffic. Now, whenever you see reference to stateful, remember in the TCP/IP suite at layer 4, TCP is your stateful protocol. So you can expect a stateful inspection firewall of any type is going to operate at least at layer 4 and potentially higher depending on the functionality that it offers. Then we have deep packet inspection firewalls. These operate typically at the application layer in order to filter the payload content of a communication rather than only the header values. Up next is stateless. Now I want you to pay special attention for the next handful here. These are the firewall concepts that should be top of mind for you on the exam. So stateless firewalls will watch network traffic and restrict or block packets based on source and destination addresses or other static values. They are not aware of traffic patterns or data flows. This does mean they are typically faster and perform better under heavier loads, frankly because they are doing less. And then we have stateful firewalls. These can watch traffic streams from end to end. They are aware of communication paths and can implement various IP security functions like tunnels and encryption. They're better at identifying unauthorized and forged communications because they are tracking the context of the conversation. A stateful firewall can follow the TCP three-way handshake. It spots half-open connections. And I would expect any firewall that organizations are using in 2024 will typically be stateful. Now we have the web application firewalls, or WAF as they're commonly abbreviated. They protect web applications by filtering and monitoring HTTP traffic between a web application and the internet. Typically protects web applications from common attacks like cross-site scripting, cross-site request forgery, SQL injection, really anything from the OWASP top 10 list of web application threats. And in fact, most WAFs you will find these days come pre-configured with OWASP rule sets. We call them OWASP CRS or core rule sets. Your cloud service providers, your Microsoft Azure, AWS, Google Cloud Platform will all offer a WAF that supports OWASP core rule sets, meaning you can put a good set of web application protections in with just a few clicks. And then we have the next generation firewall, abbreviated NGFW. This is a deep packet inspection firewall that moves beyond port protocol inspection and blocking. It adds application level inspection, intrusion prevention, and brings intelligence from outside the firewall, meaning that it generally has access to some sort of external threat intelligence feed. So as you see here, the NGFW is multifunctional, and exactly what functionality it will bring will vary a bit from vendor to vendor, but these are the core characteristics. So deep packet inspection, we've mentioned that a time or two. So this is packet inspection that inspects and filters both the header and the payload of a packet that's transmitted through an inspection point. So a deep packet inspection firewall can detect protocol noncompliance, spam, viruses, and other intrusions. Next we have Unified Threat Management, abbreviated UTM. This is a multi-function device composed of several security features in addition to a firewall. A UTM may include intrusion detection or intrusion prevention, TLS proxy, web filtering, quality of service, bandwidth throttling, NAT, VPN anchoring, antivirus. So many functions rolled up into one box means it's going to be well suited for small and medium businesses. So that's typically where you'll find a UTM. You can imagine with all of that functionality running through a single appliance, its ability to scale is going to be a bit less, but with unified management like that, it's also going to be a bit easier to manage for an IT generalist that would be common in a small business. Now we're going to move into the secure communication section of 3.2, where we see VPN mentioned. So let's start with a base definition. So a VPN extends a private network across a public network, enabling users and devices to send and receive data across the shared or public networks as if their computing devices were directly connected to the private network. That can be a user working from home connecting to the corporate office using a VPN client. That can be a hybrid cloud where we connect a corporate data center to a public cloud like AWS or Azure using a site-to-site VPN. So in that client scenario, with a remote worker, for example, we often encounter the concept of a split tunnel or a full tunnel. So full tunnel means using the VPN for all traffic, both to the internet and the corporate network. Split tunnel uses VPN for traffic destined for the corporate network only and internet traffic direct through its normal route. And many companies will use that split tunnel strategy to save bandwidth, to save resources. Assuming their endpoint security gives them enough confidence that that's a safe strategy, it's going to result in a lot less traffic coming back across the wire and traveling out the corporate pipe to the internet, which means it's likely also going to provide a better user experience for that user that's browsing the internet from home while they're working. Now, I've mentioned these two scenarios, the remote access versus site-to-site. So in the site-to-site scenario, IPsec site-to-site VPN uses an always-on mode where both packet header and payload are encrypted. We call this IPsec tunnel mode. And in a remote access scenario, that remote worker, a connection is initiated from a user's PC or laptop for a connection of a shorter duration. This is IPsec transport mode. So on the topic of IPsec, there are a couple of protocols and modes you should be familiar with. So in terms of IPsec protocols, we have authentication header and encapsulating security payload, abbreviated AH and ESP respectively. The authentication header provides a mechanism for authentication only. And because the AH option does not perform encryption, it is faster than encapsulating security payload. The ESP option provides data confidentiality through encryption and authentication, data integrity, data origin authentication, and replay protection. Encapsulating security payload can be used with confidentiality only, authentication only, or both confidentiality and authentication. And then again, just to touch on those IPsec modes. In transport mode, the IP addresses in the outer header are used to determine the IPsec policy that will be applied to the packet. That's good for ESP host-to-host traffic. That's what we'd see in the VPN client scenario for the remote worker, for example. And in tunnel mode, 2 IP headers are sent. The inner IP packet determines the IPsec policy that protects its content. This is good for VPNs and for gateway-to-gateway security. That's the hybrid cloud site-to-site VPN scenario I mentioned. Up next, we have SD-WAN, software-defined wide area networks. SD-WAN enables users in branch offices to remotely connect to an enterprise's network. It enables the use of many network services, MPLS, LTE, broadband internet, to securely connect users to applications. Security is largely based on IPsec, VPN tunnels, next-gen firewalls, and microsegmentation of application traffic. And in more recent years, what we're seeing in terms of SD-WAN configurations is a centralized control function for intelligent routing and secure access service edge to decentralize connectivity. So let's unpack secure access service edge, as this is next on the list and a fairly recent concept in the world of wide area networks and cloud. Secure Access Service Edge is a design philosophy closely related to Zero Trust Network Architecture. Abbreviated SASE, pronounced SASE, it brings together networking and security functions and delivers them as an integrated cloud service. SASE will include several components like firewall services, secure web gateway, anti-malware, intrusion prevention, a cloud access security broker, or CASB for short, as well as data loss prevention. So we have a variety of protections here, from endpoint to infrastructure to data to applications. So according to Gartner, SASE is a networking model that merges traditional WAN management and security capabilities into a unified whole. SASE is built, implemented, and managed using cloud-native architectures. It's a response to the edge-centric trends in mobility, cloud, SD-WAN, and the Internet of Things. It is still considered an emerging, evolving cybersecurity concept. It was first described by Gartner in 2019. This is a modern cloud-centric approach to SD-WAN. All right, last on the syllabus for 3.2 is selection of effective security controls. So knowing the criteria for selecting the right security controls for different threats and scenarios is absolutely key to effective security. You need to be able to match the controls to the scenario. So how do you go about doing that? Well, you need to identify the valuable assets in your environment and their vulnerabilities. So you identify your assets, potential vulnerabilities, and the associated threats. And we'll collaborate with the business on this. When we're identifying assets, we need to understand the value of those assets to the business so we can prioritize what we protect. We can identify potential vulnerabilities through vulnerability scans and assessments, and threat modeling exercises using frameworks like Stride and PASTA. Develop data flow diagrams that illustrate how sensitive data flows through our environment, through our applications, through our networks, through our systems, and perform an impact analysis. Analyze the potential impact of a security breach on each asset so we can understand what impacts the business the most, and we can set our priorities. Our goal here is not just to keep the organization secure, but to keep the business up and running, servicing customers, accepting payments. And you have to understand the types of threats most likely to target your environment, the threat landscape. So certainly there are elements that are unique to your organization, but also to your industry. So if your organization operates in the financial services vertical or the healthcare vertical, it pays not only to remain abreast of the latest developments in the security threat landscape, but the types of attacks that are most likely to target your industry. So I spend a fair bit of time working in regulated industries like financial services and healthcare, so I try to remain abreast of the latest developments in those industries so I understand how bad actors are coming after organizations in those verticals. But at the end of the day, selecting effective security controls depends on several key criteria, tailoring them to the specific environment and potential threats that are likely in that environment. And your ability to bring all these elements together comes with exposure and practice and time. And that brings us to section 3.3, where we'll compare and contrast concepts and strategies to protect data. We'll begin with a look at data types before reviewing a number of data classifications, and then moving into a category called General Data Considerations, where we're going to focus on the state of our data before we review methods we can use to secure that data. So from a process perspective, we identify the data type, apply the appropriate classification, identify the states where that data will be exposed, and then choose the appropriate methods to secure. And we see data sovereignty, geolocation, and geographic restrictions called out here in the syllabus. which I would cite as a clear nod to the importance of cloud computing in 2024 and beyond. Starting with data types, we have regulated data. This is data subject to specific laws and regulations governing its collection, storage, and use. And a few examples here would include personally identifiable information, or PII, protected health information, PHI, or financial information like credit card data. It's worth noting that organizations that fail to comply with data protection regulations with regards to regulated data like this can lead to hefty fines and penalties. Next is the trade secret, which is the intellectual property of an inventor that is absolutely critical to their business and must not be disclosed. Examples here would include formulas, product designs, customer lists. Trade secrets are valid as long as secrecy is maintained and not discovered by others. Next, we have intellectual property. These are creations of the mind, inventions, literary and artistic works, designs, symbols, names, and images used in commerce. So, intellectual property encompasses broader categories of intangible assets like patents, copyrights, and trademarks. And a data leak involving intellectual property can lead to loss of revenue and potentially permanent loss of competitive advantage. Next, we have legal information. Documents, communications, and records that are related to legal proceedings, contracts, or corporate governance. Examples here include attorney-client privileged communications, contracts, legal opinions, court records, and regulatory filings. Now we're going to take a sidebar here and discuss some intellectual property protections. There are trademarks that cover words, slogans, and logos used to identify a company and its products or services. A trademark lasts 10 years and can be renewed. A patent protects the intellectual property rights of inventors, and it provides the inventor exclusive use of their invention for a period of time, generally 20 years, but the filing requires public disclosure. And granting of a patent is not automatic. There are certain requirements of utility and uniqueness in order to obtain a patent. I'm going to repeat trade secret here briefly because it is an intellectual property protection that protects the property of the inventor and must not be disclosed. So there's no filing requirement for a trade secret, but it's valid as long as secrecy is maintained and not discovered by others. You cannot go to the Patent and Trademark Office and register a trade secret, but there are 3 requirements. The information has to have economic value. It has to be information not readily known by others, and you have to take the proper steps to maintain confidentiality of the information. And last on the list here is copyright. A copyright is automatically granted to the creator of a work upon creation, but it can be registered, and that prevents others from reusing the creation. Protection lasts 70 years beyond the creator's death, then the work moves into the public domain, where reuse is then allowed. Back to our list, we have financial information. Any financial records maintained by the organization or data related to financial transactions, assets, and liabilities. Examples of financial information include investment records, bank account details, credit card numbers, and these may be subject to Graham, Leach, Bliley, or PCI DSS regulations. And last on the list of broad types is human and non-human readable. So human readable is just what it sounds like, data that can be directly understood by humans without special tools like text documents, images, and videos. Non-human readable is data that requires specific software or tools to be interpreted, like machine code, database files, encrypted data, anything you can't just pick up and read immediately. Now we're going to move into data classifications, and I'm going to begin with a look at a chart reflecting some U.S. government classifications and their non-government, public, or commercial equivalents. So at the lowest level of sensitivity, class 0 here, we have unclassified on the government side, public on the commercial side, where exposure, of course, results in no damage because it's public data. Then we have confidential or sensitive, where some damage to the organization results when that data is leaked or made public otherwise. We then have secret and private, which is a bit more serious when leaked. And then at the top of the pyramid here, we have top secret and confidential or proprietary on the commercial side. But you notice the equivalence here in terms of damage. So we see serious damage and then exceptionally grave damage at the highest level. That's a chart that you'd see preparing for a security leadership exam like the CISSP. Now let's take a look at the data classification terms that show up in the exam syllabus. So we have public data, which is freely accessible information intended for the general public. Examples here would include brochures, press releases, public-facing website, government data portals, but no privacy or compliance concerns whatsoever. Next, we have private data. So this is information about an individual that should be kept confidential. This would include personally identifiable information or protected health information. But private data is a broad category that really speaks to any type of personal data. Next, we have confidential data. This is data that an organization intends to keep secret within a designated group. So examples here would include salary data, trade secrets, internal memos, customer lists. So not only is that data kept private within the company, but it's going to be access restricted to authorized personnel based on their role. Next, we have restricted data. This is data subject to external regulations or legal requirements that limit access and control its handling. So regulated data, for example, would include protected health information subject to HIPAA regulations. And it's worth noting that confidential data can also be restricted data if it's governed by specific laws like HIPAA or PCI DSS. Next, we have sensitive data. This is information that's not publicly known, and it requires careful handling due to its potential for harm if exposed. So sensitive data encompasses private, confidential, and restricted data, but it also includes strategic plans, intellectual property, and other information critical to an organization's operations. Next, we have critical data, information essential for the success of a specific mission or core function within the organization. Loss or disruption could significantly impact the organization's ability to achieve its goals. Examples here would include financial records, customer databases, operational control systems, and research data. Now I want to take a sidebar here and unpack two examples of sensitive data that I think you should be familiar with for the exam, and it'll be generally helpful as you navigate the world of cybersecurity. We have personally identifiable information, PII, which is any information that can identify an individual, like a name, social security number, birth date, and place, any biometric records or data. The other most common one is protected health information, which is health-related information that can be related to a specific person. PHI is protected under HIPAA regulations. To wrap up data classifications, I want to talk through the consequences of data leak or data loss. So certainly we have financial loss, operational disruption, reputational damage. In the case of data that's regulated under law, potential legal repercussions. There's the potential for loss of competitive advantage in the case of trade secrets or intellectual property leak, and the loss of copyright, patent, or trademark protection leading to potential infringement by competitors. You may remember those are protections we talked about surrounding intellectual property, and a simple leak wouldn't automatically result in the loss of copyright, patent, or trademark necessarily, but oversharing through a leak or theft definitely opens the door to some problems. Moving on to general data considerations. You'll want to be familiar with how we can encrypt different types of data at rest. So for example, in the cloud, the answer is often storage service encryption. Your CSP storage providers usually protect data at rest by automatically encrypting before persisting it to manage disks, blob file, or queue storage. There's generally an option for you to add an extra layer of encryption with your own customer-held keys, what's referred to as double encryption, depending on the CSP, but your CSPs usually have some encryption there by default at rest in 2024. There's full disk encryption, which helps you encrypt Windows and Linux ISVM disks using BitLocker on the Windows platform and dmcrypt, which is the Linux equivalent, for your OS and data disks. So those are generally available on Windows and Linux clients and servers, on-prem or in the cloud. That's an OS level feature. There's transparent data encryption, simply called transparent encryption on some relational database management platforms, that helps protect SQL database and data warehouses against threat of malicious activity, with real-time encryption and decryption of database backups and transaction log files at rest without requiring app changes. You should also be familiar with encrypting data in motion. So data in motion is most often encrypted using TLS or secure HTTP. This is typically how a session is encrypted before a user enters credit card details, for example. And while you may hear SSL referenced when we're talking about encrypting traffic on the network, it's similar in function, but TLS, Transport Layer Security, has replaced SSL at this point. And the third state you should be familiar with is data in use. So data in use, sometimes called data in processing, occurs when we launch an application like Microsoft Word or Adobe Acrobat. But we're talking about apps not running the data from the disk drive, but running the application in memory. This is volatile memory, meaning that should you power down the computer, the contents are erased. It's worth mentioning at an operating system level, some bits of confidential or sensitive information are stored in memory as well, such as password hashes when you are working on a Windows computer. And in that case, it's a matter of knowing what is available to you to protect that information further. So for example, Credential Guard, which encrypts password hashes in memory on Windows, is an example of technology that can protect data in use. Not the only protection, but just one of those areas we want to think about. In that particular case, the password hashes are rendered worthless because Credential Card encrypts those. So when an attacker manages to get to those hashes in memory and dump them, they're encrypted and worthless. And there are two more concepts we want to cover here in general data considerations. The first is data sovereignty. So your digital data is subject to the laws and regulations of the country in which it was created, and often it cannot be moved to another region, even for a backup-related reason. At the same time, data is subject to the laws of the country where it is stored, which can bring significant legal implications, including demands from that company's legal system to produce that data as part of litigation. So a company's legal department should be consulted to offer guidance on the legal impact of geography on data sovereignty. This can definitely come up in disaster recovery scenarios when you're working in the European Union, where you may have a primary and backup data center that are in different countries. But moving data out of the EU does not remove the GDPR requirements, for example. Data that belongs to an EU citizen is still going to be subject to GDPR, even if you're storing it in the United States. The other concept we see mentioned here to wrap up general data considerations is geolocation. Geolocation uses GPS to give the actual location of a mobile device. IP address is used sometimes, but it's not as accurate because IP addresses can be spoofed. But geolocation can be very useful if a device is lost or stolen. And it's often used to guide a decision to restrict data access or wipe a mobile device. Many of your modern identity providers, in providing multi-factor authentication, will allow us to consider the context of the request to include the user's device and their location, and allow us to then potentially restrict access or request an additional authentication factor just to make sure we have the user we believe we have. This is known as somewhere you are when evaluating an authentication request. Moving on to methods to secure data. We're going to begin with hashing and encryption, and I like to cover these two together so we can talk about how they are different, and it will help anchor these in your mind for exam day. So first we have encryption. So encryption is a two-way function. What is encrypted can be decrypted with the proper key. So common uses of encryption include bulk data encryption, which is symmetric encryption or shared key, and secure transactions and digital signatures use asymmetric encryption, which involves a public key and a private key. And we'll get deeper into encryption elsewhere in this series, but that's the high level. And then we have hashing, which, unlike encryption, is a one-way function that scrambles plain text to produce a unique message digest. So a hashing algorithm involves a conversion of a string of characters into a shorter fixed length value. So no matter the length of the input, the output is always going to be the same fixed length value. And for any given unique input, the output should also be a unique hash. And there's no way to reverse a hash if properly designed. It's a one-way function. Common uses would include file or data integrity verification, digital signature integrity, password storage. For example, as part of a process to copy a file from our on-premises data center to the cloud, we could write into our script to produce a hash of that file before it's transferred, hash it again after it's transferred, and compare the two to make sure they match, thus verifying the integrity of the file, that it arrived intact. Next, we have data masking. This is when only partial data is left visible in a field. For example, a credit card may be shown with only the last 4 digits visible. And data masking is very commonly implemented within the database tier, but it's also possible in code in front-end applications. So when you call into your credit card company and they ask you to perhaps verify the last 4 digits of a credit card, it may be that the agent in the chair can only see the last 4 digits. If you're verifying the last 4 digits of your social security number, that's almost certainly true. Next, we have tokenization. This is where meaningful data is replaced with a token that's generated randomly, and the original data is held in a vault. So for example, a user's identity might be replaced by a token, and the user's identity is stored in that vault, and that's the translation. This is considered stronger than encryption, and the keys are not local. And then we have pseudonymization, which is a de-identification procedure in which personally identifiable information fields within a data record are replaced by one or more artificial identifiers or pseudonyms. Reversal requires access to another data source. Next, we have anonymization. This is the process of removing all relevant data so that it is impossible to identify the original subject or person. This is only effective if you do not need the identity data. Next, we have geographic restrictions, which limits access to data based on the user's physical location. It involves restricting access attempts originating from certain countries or IP addresses, aiming to prevent unauthorized access from specific regions. And this is a technique often used by organizations with regulations or security concerns specific to certain geographic areas. And next we have obfuscation, which involves intentionally making data less readable or understandable. And it's a broad term that refers to several techniques. For example, techniques like code obfuscation or data masking, which we looked at a moment ago, can be used to obscure the original data while retaining its functionality. It helps prevent unauthorized users from easily interpreting or extracting sensitive information, even if they gain access. Next, we have segmentation, which is a method that involves dividing data into smaller, isolated segments. This can be achieved through data partitioning or logical separation within storage systems, and it can limit the impact of a potential security breach, as only a specific segment might be compromised instead of the entire dataset. And finally, we have permission restrictions, also known as access control. This one is very common. It controls access to data based on user roles and permissions. So access control systems define what users or groups can access specific data elements or functionalities. For example, role-based access control, or RBAC as it's often called on Windows. It ensures that only authorized individuals have access to sensitive information based on their designated roles and responsibilities. Now, to help tie all these concepts together, I want to walk you through the data lifecycle. So the life of data from a functional perspective. So a data's life, of course, begins at creation. Data can be created by users. A user creates a file. It can be created by systems. A system logs access. Then should come classification. So to ensure it's handled properly, it's important to ensure that data is classified as soon as possible. Next, we have storage. Data should be protected by adequate security controls based on its classification. That can mean various forms of encryption and access control based on how we classified it. Next, we have use. This refers to any time data is in transit over a network. You'll generally hear this called data in transit or data in motion. And we have archival. So archival is sometimes needed to comply with laws or regulation requiring the retention of data. A data retention policy ensures a company retains data as long as necessary, and that's a key phrase. As long as necessary is defined by company policies or regulatory requirements. And when we come to the end of as long as necessary, it's important that we destroy that data. So when it's no longer needed, it should be destroyed in such a way that it is not readable. And that means not recoverable, even through forensic means. Remember, data kept for longer than it's needed creates additional risk. Data we do not have cannot be leaked, it cannot be stolen, it cannot be produced for litigation. That brings us to section 3.4, where we'll focus on resilience and recovery. More specifically, we're expected to explain the importance of resilience and recovery in security architecture for the exam. So in this section, we'll explore high availability concepts, site considerations, including the types of disaster recovery sites we might choose from, the importance of platform diversity, multi-cloud systems, and continuity of operations. We'll take a look at capacity planning concerns, the different disaster recovery testing types, an array of backup strategies, and finally a look at power. Before we do, though, I want to unpack those two terms we see in the title of this section, resilience and recovery. I don't want to take for granted that we know the details of these two and the difference between them. Resilience speaks to the ability of a system to remain functional even when faced with unexpected events like natural disasters or cyber attacks that lead to disruptions and failures. Resilience is delivered through redundancy in systems and failover mechanisms in the event of system failure. But this is a security exam, so let's get a bit more specific. Cyber resilience refers to an organization's overall ability to prevent and withstand cyber threats and incidents. It's about ensuring continuity of operations even during attacks, disruptions, or outages. And then we have recovery, which focuses specifically on the restoration of data and systems after a cyber attack or incident. Stated a bit more simply, it's the process of getting things back to normal after a disruption. So some of the key elements of recovery include backup, disaster recovery, business continuity planning, testing, and validation. We will certainly touch on backup and testing in this section, and we'll dig into disaster recovery and business continuity planning at greater depth later in the series. But since resilience and recovery are the two elements we're evaluating throughout this section, I want to just paint a picture for you here. So think of resilience and recovery as two sides of the same coin. Cyber resilience is the shield. It protects your organization from attacks and minimizes the likelihood of successful breaches. Cyber recovery is the repair kit. It allows you to fix the damage and get back on track after an incident. The goals here are to improve the organization's overall cybersecurity posture and to ensure business continuity even in the face of cyber threats. So you might think of resilience as being a proactive measure and recovery being a reactive measure, though we're going to take some proactive steps to prepare for recovery to ensure we can recover should the situation call for it. So let's get into high availability. And we'll start with load balancing, which distributes network traffic across multiple servers, ensuring optimal performance and high availability. So from a resilience perspective, it distributes the workload by spreading traffic across multiple servers. Load balancing prevents overloading any single server, ensuring continuous operation even if one server fails. Load balancing also simplifies scalability. It allows easy addition of new servers to handle increased traffic, enhancing responsiveness and preventing bottlenecks. Generally speaking, when I want to add a new server to a load balance web farm, it's a pretty easy operation. I plug the server in, I add an entry to my load balancer table, and I'm all set. And it allows us to scale out, adding additional servers, which is a less expensive strategy when we're using that in the cloud. So we can add additional servers when we need the additional capacity, or at least shut them down and start them up, rather than simply oversizing a smaller number of servers with excess compute, which in the cloud we'd have to pay for. So let's look at load balancing from a recovery perspective. So we get faster failover. When a server fails, the load balancer automatically directs traffic to remaining healthy servers, facilitating quicker recovery and minimizing service impact. And it simplifies recovery. By isolating individual failed servers, load balancing simplifies the process of identifying and addressing the issue on the failed server without affecting the entire system, because the load balancer removes failed servers from the list of available servers in the farm that are receiving requests because they fail the health check. And load balancers are commonly used with front-end web and application servers. So hopefully the type of health check is one that makes a call to the application to make sure that it's serving up content and it's not just a simple ping check. So let's move on and talk about high availability in the context of clustering now. So clustering combines multiple servers into a single, highly available entity, ensuring continuous service even when individual servers fail. So from a resilience perspective, we have hardware redundancy, so it creates a single logical entity from multiple servers with shared resources and data. Traditionally, we'd configure server clusters with shared data behind them. Increasingly, that's not always necessary nowadays, but oftentimes there are shared resources and data on the back end, and if one server fails, the others can take over the workload, take control of the storage, continue to serve up data and resources. So we're also getting high availability here. It provides continuous uptime even during individual server failures, preventing any disruption to service. And from a recovery perspective, we get automatic failover. Basically, when a server fails, the remaining servers automatically take over its tasks, ensuring seamless service continuation and minimal user disruption. You typically put an odd number of nodes in a server cluster and they establish a quorum, and when a majority can't contact a specific server, they take it out of the cluster and continue service without it. And oftentimes, we'll see data replication come into the picture. So it's often implemented with clustering to ensure that data is stored on multiple servers, allowing for quick restoration in case of data loss on a single server. But we'll also often see data replication to a cluster at a recovery site, which potentially gives us a way back if there's something very unexpected that happens with that cluster on the whole. For example, if that cluster uses shared storage and we have a major storage problem that causes all the servers to go offline. But you'll see clustering typically used with back-end database servers. So if you have a web application with back-end databases, you're typically using load balancing of a web farm or an application server farm up front, and you're using clustering for your databases in the back. So using physical or virtual servers in both front and back end, but how you establish that high availability is different based on their role. Okay, next on the syllabus is multi-cloud systems. So from a resilience perspective, what we're talking about here is distributing data and applications across multiple public cloud providers to create redundancy and fault tolerance. So if one cloud provider experiences an outage or an attack, the others can maintain service for us. It allows us to keep the trains running, servicing customers, while we recover whatever has failed in that affected provider. And from a cyber attack perspective, it indirectly works as a method of segmentation, because when AWS is affected, Azure and Google Cloud Platform would likely remain unaffected. But from a recovery perspective, this buys us a great deal because it enables rapid failover to unaffected cloud platforms, minimizing downtime and facilitating faster recovery from security incidents. This might mean simple DNS failover, or we can actually deal with failover automatically in some cases with global load balancing strategies. We could even implement a global server load balancing strategy with a third party like Cloudflare, so we can route across all of our public cloud providers, basically sending traffic to healthy server pools no matter which cloud they're located in. From a cyber risk perspective, what multi-cloud does is mitigate the risk of vendor lock-in and provider-specific security vulnerabilities. In this same vein, let's talk about platform diversity. So platform diversity very much mimics what we talked about with multi-cloud, but it focuses on utilizing a mix of different platforms. We're talking about operating systems, software vendors, cloud providers, so it's a broader strategy, right, that reduces reliance on any single point of failure, any single vendor. If one platform or provider experiences an outage or a security breach, the others continue functioning, minimizing disruption. And same sort of strategy. It allows us to recover more quickly by allowing operations to shift to unaffected platforms while the compromised one is addressed. And it mitigates platform-specific vulnerabilities or attacks. So whether it's a SaaS provider or a public cloud platform or a sudden zero-day threat on a Windows or Linux operating system, we're mitigating the risk. Next, we have continuity of operations. So from a resilience perspective, what this means is planning, outlining procedures and resources to maintain critical business functions even during disruptions. This would include backup and disaster recovery strategies, alternative communication channels, and other disaster recovery protocols. So this is all proactive work to ensure that when recovery happens, we have a swift and efficient recovery process, minimizing downtime and financial losses after security incidents. Basically, ensuring that operations response is successful, reducing the potential for loss of any kind, whether data, financial, or something else. Okay, now we're going to move on to site considerations. Recovery sites are secondary locations where critical IT infrastructure can be restored, ensuring business continuity after a major disruption at the site level. So in terms of resilience, recovery sites give us a contingency plan. It provides a backup option in case of catastrophic events like natural disasters or cyber attacks that affect an entire site. Simply put, it minimizes downtime due to site failure, and it enhances our preparedness for these types of events. It improves the organization's ability to maintain business continuity through unforeseen circumstances. And from a recovery perspective, it gives us faster restoration. It allows for quicker resumption of critical operations compared to rebuilding everything from scratch at the primary site. And it also gives us reduced downtime. So it minimizes the impact of disruptions on business activities and revenue generation. Now, to be clear, budget and availability needs will dictate the type of recovery site we implement, or recovery sites. So from that perspective, we see three types of sites called out in the syllabus, and those are hot, warm, and cold sites. And there's room for a lot of nuance in creating hot, warm, and cold sites. They're not all the same, but I'm going to give you the high-level definitions that will allow you to focus in on the core intent for the exam. So let's start with the cold site. So this is a recovery site that is essentially just data center space, power and network connectivity ready and waiting when you might need it. So to recover, if disaster strikes, your teams can basically move your hardware into the data center and get you back up and running. So from a cost perspective, it's low. From an effort perspective, it's high because we just have the space. Moving on to the warm site. So a warm site is more preventative in nature. It allows us to pre-install hardware and pre-configure our bandwidth. So to recover, all we have to do is load our software and data to restore our business systems. So the cost is going to be a bit more and the effort is going to be a bit less versus the cold site. So I'd say cost and effort are both in the medium category. And finally, we have the hot site. A proactive hot site allows you to keep servers and a live backup site up and running in the event of a disaster. You replicate your production environment in that data center. And to recover, we have a near immediate cutover option when we have an affected site. So in the case our primary goes down, cutover should be momentary. So for mission critical sites and mission critical customer facing services, a hot site is considered a must for organizations that can afford it. This is going to be the highest cost, but the lowest effort in recovery when it's time to execute. The last item on the discussion list for site considerations are geographic considerations for our recovery sites. We need to think about our data, systems, services, as well as the personnel who will execute the recovery operation. So distance is certainly a concern. And while the fastest site to restore services is a hot site, a site hundreds of miles away is sometimes impractical or inconvenient in some respects. But location is important. The location of the hot site is critical to the speed of data, system, and service recovery. Now, the considerations for personnel may vary because we can often work remotely. And that location should be far enough away to ensure recoverability in the event of a natural disaster like a hurricane or a tornado. And your public cloud providers are a great example to follow. Your CSPs definitely ensure they're far enough away for recoverability when they pick their own primary-secondary pairs. In fact, they typically maintain 300 plus miles between sites. So it's pretty common that for a cloud service provider in the public space like AWS or Azure, they'll have a primary site, say, on the East Coast, and the secondary failover site will be on the West Coast. And especially if you're in a hybrid or private cloud situation, you have to think about off-site backups. We have to have backups off-site, meaning physical backup media should be stored in a fireproof safe somewhere or safely in the cloud if it's still digital. And I would say today that is the most common approach. It's pretty rare that we see folks using tape all that much anymore. And similarly, disk-based backup should be stored off-site in a cloud or other secure remote repository, but cloud services are a very common solution today. Next up is capacity planning, and the capacity planning topic has 3 subcategories listed on the syllabus: people, technology, and infrastructure. So let's start with the definition. What is capacity planning exactly? Well, it is the process of proactively assessing and ensuring an organization has sufficient resources, like people, technology, and infrastructure, to meet current and future demands, preventing performance bottlenecks and service disruptions. Preventing is a key word there. So let's start with people. We need to ensure that the workforce possesses the necessary skills and knowledge to maintain secure systems and to respond to security incidents. And we also need to make sure that the workload is manageable. We need to manage staffing levels, turnover, and sharing that workload across the team to optimize results. At the end of the day, the goal is a skilled workforce who can identify and mitigate security threats. And next we have technology. So we need to ensure that the software and tools with appropriate features like automation to enable analysts to manage incidents at scale are in place. Implementing and maintaining appropriate security software and tools like firewalls, intrusion detection and prevention, anti-malware, vulnerability scanners. At the end of the day, these security tools enable the security teams to respond appropriately at scale. And the right tooling with the right capabilities and enough licensing to run those legally is very important. And then we have infrastructure, so ensuring adequate system level resources, storage, networking, processing to handle peak loads. So ensuring elasticity to respond to sudden spikes, like in the midst of a disruptive attack of scale, like distributed denial of service. This enables faster response and reduces the potential for loss of any kind, data, financial, or otherwise. The next category on the syllabus is testing, but it's clear that we're talking about types of incident response exercises here, and there are 4 that you should know for the exam as called out by the syllabus. There's the tabletop exercise, sometimes called a structured walkthrough, where you distribute copies of the incident response plans to the members of the incident response team for review. The team members provide feedback about any updates needed to keep the plan current. It's something that usually happens in a conference room together. It's paper-based, it's hypothetical, it's talking only. Usually only the person leading the tabletop exercise knows what they're going to be talking about before the meeting. And that person will put some sort of scenario out there and the team will talk through the response plan. Then we have the failover plan. This is where tests actually shut down the primary site and test whether the recovery site properly handles the load. So, of course, this should be carefully planned and scheduled as they can impact production operations. And then we have the simulation, which are functional exercises that allow personnel to test the plans in a simulated operational environment. These functional exercises range from simple simulations to full-blown tests without affecting production systems. The tests will cover specific pieces of failover in a simulated environment is the key here. Meaning doesn't touch production. And then we have parallel processing, which ensures the disaster recovery site is actually working by activating it during the test. So during the test, the recovery site starts operations and runs alongside the main site in parallel, which enables testing the plan in something that feels like a full test, but with less risk than a simple full failover. Now we're going to move into the backups category, and you need to know what each of these backup types do, but also why they are important to security. So I'll fill in the gaps on all counts here. So backups can be on-site or off-site. So your on-site backups are stored on the same physical location as the original data, like an external hard drive. Off-site backups are stored in a separate location, cloud storage, remote data center, secure off-site storage purpose-built for storing media of that type. And then there's the backup frequency, which refers to how often backups are performed. It might be daily, hourly, continuously. The frequency really depends on the importance of the data, the amount of the data changing, acceptable levels of data loss, and for critical data that allows us to keep the business running, the backup schedule is going to be more aggressive. And we'll talk about recovery time objective and recovery point objective, RTO and RPO, later in the series in some depth. But your backup strategy is going to be influenced by the amount of data you're backing up, the amount of data churn there, and how much time and data we can lose in case of a disaster and still resume business in a new location or on a new system. Next we have encryption. So this is the process of scrambling data into an unreadable format requiring a decryption key for access. Sensitive backups should not be left in a plain text format. They should not be plain text human readable. Next we have the snapshot. These are point-in-time copies of data at a specific moment, allowing recovery to a specific state. Snapshots are very common with VMs and with high-end storage area networks. So we need to think about recovery, the process of restoring data from backup to its original location or a new location. And this really refers just to understanding the process of restoring data from the backup. There needs to be some advanced planning, some of that recovery planning to make sure that we understand what the potential needs are in different scenarios. Are we always going to be recovering to the original location? Do we need a strategy to recover to the new location in a specific amount of time? We have replication, creating identical copies of data in multiple locations for redundancy, and journaling, transaction logging, recording all changes made to data in a sequential log file. And this log can be used to recover data to a consistent state by replaying the log transactions, enabling point-in-time recovery or roll-forward recovery. But that replaying of log transactions is actually pretty common with some relational database recovery strategies. So point-in-time recovery would recover the database to a specific point in time, and roll-forward recovery would bring it up to typically like right before the moment of the critical failure. So we've talked about the what when it comes to backups. Now let's talk about the why. So why are backups important to security? Well, naturally, backups are crucial because they provide a way to recover data lost due to various security threats. So it may be accidental deletion, hardware failures, or very intentional, like ransomware attacks or other incidents. Backups give us a means to restore data and minimize the impact. And some cyber attacks, like malware and ransomware attacks, ransomware in particular, often encrypt or corrupt data, making it inaccessible. Backups stored securely off-site can provide clean copies for recovery. Stored in the cloud may allow us to recover cleanly more quickly. Compliance requirements can also mandate data backup and retention for specific periods. So backup ensure compliance with these regulations. And if you're asked on the exam, a full backup provides the fastest recovery time. The real answer is going to depend on the nuance of the situation, but on the exam, if you get a generic question about fastest recovery time, it's almost certainly going to be full backup they're looking for. I think we've covered the spirit of these all already, but I'm just going to roll back some scenarios here so you've got them written down in one place as you prep for the exam. So ransomware attacks. After a ransomware attack, backups allow for data restoration without paying the ransom. Super important. Very likely real-world scenario. Disaster recovery. So in case of natural disasters or infrastructure failures, offsite backups ensure data availability. Accidental data deletion. Data corruption, so we can use backups to restore data corrupted by malware or even hardware malfunction. And I mentioned compliance. We could also use backups for compliance audits to demonstrate adherence to data retention policies and regulations. What you'd see in an audit scenario is a request from the auditor to restore a specific piece of data from a specific point in time. So we'll wrap up 3.4 with a look at power. So we're going to talk about the need for clean power. So power supplied by the electric companies is not always consistent and clean. Most electronic equipment we're working with in a data center requires clean power in order to function properly and avoid damage. So a UPS is a type of self-charging battery that can be used to supply clean, consistent power to sensitive equipment and supply that power for minutes or hours depending on its size in the event of power failure. But it's important we understand the difference when it comes to power redundancy between the purpose of a UPS, the uninterruptible power supply, and a generator. So a UPS is essentially a battery that is a standby device so that when primary power fails, it provides power. It's really designed to keep the systems running for a limited period of time, though, basically to enable graceful system shutdown. It's also used to clean up the power coming from the grid, eliminating spikes, surges, and voltage fluctuations. It protects systems and data from damage. We then have the generator, which is a standby power source that is powered by diesel, gasoline, propane, or natural gas. And when power from the grid fails, it can be started to provide electricity for an extended period of time. Generators are used by hospitals, data centers, and other facilities hosting critical services. But a generator provides sustained alternate power to support continued operation, not just graceful shutdown. So the UPS, while it's cleaning up power, preventing surges and voltage fluctuations, in the event of a failure, it's short term. It's minutes or maybe hours. The generator is going to be longer term, hours or even days. But in either case, it allows us to respond more effectively and gracefully to an unexpected loss of power, regardless of the reason, resulting in a reduced risk of data loss and a reduction in the time of our service outages, or potentially avoiding that outage altogether. Congratulations, you've reached the end of Domain 3 of the Security Plus Exam Cram series. I hope you're getting value from the series. As always, if you have questions, leave it in the comments section below or reach out directly on LinkedIn. And I'll look forward to seeing you back here in a couple of days for the launch of Domain 4. And until next time, take care and stay safe.